Hi everyone. In this lecture, I will be explaining the voltage gated ion channels present over the cell membrane of the excitable tissues. We will consider a nerve cell, neuron, as an excitable cell. The cell membrane of this neuron will have voltage gated channels. So what are these voltage gated channels? These are transmembrane proteins or integral membrane proteins of the cell membrane. We know the cell membrane is a lipid bilayer, phospholipid bilayer containing the lipids, phosphates and fatty acids, and also the proteins which are transmembrane, integral, and some are extrinsic protein, some are intrinsic proteins. These transmembrane proteins are acting like channels. These transmembrane proteins are acting like channels for the movement of ions across the cell membrane along the concentration gradient. And some of these transmembrane proteins, they have gates. They have gate-like extensions. These gates can be closed and opened. So these gates, which can be opened or closed, and they are responding to change in potential difference, we call them as voltage gated channels. So gate like extensions of the integral protein, which can be opened and closed by the change in voltage. By the change in voltage across the cell membrane, we call it as voltage gated channels. Consider now there are different types of voltage gated ion channels over the cell membrane. We'll give an example of voltage gated sodium ion channels. So this is a transmembrane protein across the cell membrane. So this is a cell membrane and this is the transmembrane protein, and this will have a gate. There are two gates for this voltage gated sodium ion channels. The one gate which is outside is activation gate, and this activation gate is closed, and the gate which is inside is inactivation gate, and this inactivation gate is opened. So this is a diagram for explaining voltage gated sodium ion channel at resting state. So this is the resting state of voltage gated sodium ion channel, where activation gate is closed, activation gate is closed, whereas inactivation gate is open. And the state of this voltage gated sodium ion channel is resting state. So at resting state, do you think there is permeability for ions across this voltage gated sodium ion channel? No. The sodium, which is more in concentration outside the cell in the ECF, cannot enter the cell across this voltage gated sodium ion channel because the activation gate is closed. So this form of state of the voltage gated sodium ion channel is at minus 70 millivolt during resting membrane potential state. So this is the resting state of ion channels. So now how these voltage gated sodium ion channels respond to change in membrane potential, we'll discuss now. See, whenever there is change in membrane potential from minus 70 millivolt by the application of threshold stimulus, what is happening? The sodium ion starts entering into the cell. So this is not through the voltage gated sodium ion channels, but they're through the non-gated leaky sodium ion channels. So through the non-gated leaky sodium ion channels, what is happening? Some amount of sodium ions will start entering into the cell. So that will take the resting membrane potential from minus 70 millivolt to a firing level, that is minus 55 millivolt. So once the firing level threshold potential is reached, so at that point voltage gated sodium ion channels activation gates flip open. So voltage gated sodium ion channels activation gates flip open at a threshold potential of minus 55. So what is happening? The change is So this is the voltage gated sodium ion channel transmembrane protein. And what is happening at minus 55 millivolt, the activation gates opens. Inactivation gate is already open. So this resulting in opening up of sodium ion channel, resulting in rapid influx of sodium along the concentration gradient into the cell. Sodium can start entering, bringing the positivity into the cell. So this will result in depolarization of the cell membrane. Entry of sodium ions through the activated or opened voltage gated sodium ion channel will result in depolarization of the cell membrane. So depolarization phase, ionic basis, the reason is activation or opening up of activation gate of the voltage gated sodium ion channel. Why this activation gate is opening? Activation gate is opening because it is responding to the change in membrane potential, or it is voltage gated ion channel, and the gates are responding to the change in voltage. So when the membrane potential is from minus 70 millivolt is reaching to a threshold or firing level, membrane potential voltage reaching to the minus 55 millivolt, at this voltage the gate protein undergoes some conformation changes and it starts flipping, opening from close to open. So that is how opening up of the activation gate will result in influx of positive charged ions, sodium ions into the cell, will result in membrane depolarization, that is generation of action potential. So because of sodium influx, that will take the membrane potential up to plus 30 millivolt. So from minus 55 millivolt to plus 30 millivolt is because of the influx of sodium ions across the cell membrane through voltage gated sodium ion channels, and the voltage gated sodium ion channel is in activated state. So this is activated state of sodium channel, voltage gated sodium channels. So in the activated state, the activation gate is open, inactivation gate is anyways already opened. So why activation gate is getting opened? Activation gate is getting opened because it is responding to the change in voltage or responding to change in the membrane potential. So when the membrane potential from the resting level of minus 70 reaches to minus 55 millivolt, so at this potential the activation gate responds and it starts opening. So activation of this voltage gated sodium ion channel will result in influx of sodium ions, resulting in depolarizing potential, depolarization from minus 55 millivolt resting membrane, the membrane potential from firing level will reach to plus 30 millivolt. So at plus 30 millivolt, what is happening? It is not going towards more and more positivity. By the time it reaches plus 30 millivolt, there is some changes happening within the voltage gated sodium ion channels. So what is happening here? The inactivation gates closes. The inactivation gates closes. Activation gate is anyways opened. Inactivation gates closes. So because of this, the sodium cannot enter into the cell anymore. Sodium cannot enter into the cell anymore. So at plus 30 millivolt, because of inactivation, because of inactivation of voltage gated sodium ion channels, that is closure of inactivation gate resulting in inactivated state of this sodium ion channel, so that no more positive sodium ions can enter into the cell. So from plus 30 millivolt it cannot move upwards towards more and more positivity, so it arrests at plus 30 millivolt. And simultaneously what is happening, there is opening up of potassium channels. So consider this is the potassium channel. At rest, this channel is closed. Potassium channel is having single gate in at the inner side of the channel. The potassium cannot enter the cell when the gates are closed. So at the plus 30 millivolt, at the peak of depolarization, what is happening? There is change in response of the voltage gated potassium ion channels at that level, resulting in opening up of gates of potassium channel. So when the gates of potassium channel open, along the concentration gradient from inside the cell to the exterior, the potassium can go out. So efflux of potassium ions along the activated voltage gated potassium channels will bring the membrane potential from positive plus 30 towards downwards to resting level. And this potassium ion channels are slow to open. They open at plus 30 millivolt. They open at plus 30 millivolt, and they keep opened for longer duration, so that more and more positive charge is moving out of the cell, so that the resting membrane potential is restored. From plus 30 millivolt it comes back to minus 70 millivolt, and also from minus 70 it can go up to more and more negative, minus 75 millivolt, that is hyperpolarizing potentials. So the activation of voltage gated potassium ion channel will result in initial rapid repolarization followed by slow repolarization and hyperpolarization. So three mechanisms. What I am explaining is initial rapid repolarization, quickly repolarization because of along the concentration gradient, potassium efflux is more. Along the concentration gradient, potassium efflux is more, and quickly there is initial rapid repolarization from plus 30 millivolt to around minus 55 millivolt, and from minus 55 millivolt there is even continued repolarization, continued potassium efflux, restoring the membrane potential from minus 55 to minus 70 millivolt. So this is slow repolarization from minus 55 millivolt to minus 70 millivolt is slow repolarization. And even when the resting membrane potential is attained, there is no inactivation of potassium channel. The potassium channels are still open, so that more and more positive ion potassium ions move out. So there is hyperpolarization from minus 70 resting state to minus 75 millivolt. At minus 75 millivolt here, the voltage gated potassium ion channels closes. So voltage gated potassium ion channels closes, it goes back to its resting state. So this is the resting state, gate closure happens, and no more further efflux of potassium ions happens at this point. So after hyperpolarization is complete, the voltage gated potassium ion channel gates closure happens, the potassium efflux stops. See now how these inactive state of sodium ions, when they restore back to its resting state, we need to understand now. So the voltage gated sodium ion channel is in inactive state. Where it is in inactive state? At plus 30 millivolt. After complete depolarization at plus 30 millivolt, the voltage gated sodium ion channels is in inactive state. So because of this inactivation of voltage gated sodium ion channels and activation of voltage gated potassium channels, repolarization is happening. So during repolarization, so when the membrane potential is returning back to its resting levels, what is happening? The voltage gated sodium ion channels again respond by returning back to its resting state. So resting state means the inside gate, that is inactivation gates, slowly opens and activation gates closes. So this is the resting state of the voltage gated sodium ion channels. So voltage gated sodium ion channels return to the resting state only when the membrane potential is restored to resting levels. So that means if at all a second stimulus is applied, when already the membrane is excited, and already the voltage gated sodium channels are in inactive state or in active state, these will not respond to the second stimulus. So that will result in refractoriness or refractory period to the subsequent second stimulus. So on application of the second stimulus, do the membrane respond by generation of second action potential is question. So the membrane, in order to generate the second action potential, the membrane potential has to be restored to resting level only. Only when the membrane potential is restored to resting level and the voltage gated sodium ion channels are in resting state, then only these voltage gated sodium ion channels respond to the stimulus and generation of next action potentials. So the refractory period is a time interval during the action potential because of the first threshold stimulus where there is no generation of second action potential or response to the second stimulus. The second stimulus cannot generate the action potential because all the sodium ion channels, either they are in inactive state, all the sodium ion channels are in inactive state, and in inactive state the second stimulus, whatever may be the strength of the second stimulus, that cannot open up the inactivation gates, remember this. So inactivation gates will be opened by time dependent and restoration of membrane potential. Only when the membrane potential is restored, the inactivation gate is opened, and only after then the membrane will respond to the second stimulus. Is that clear? So this is all about voltage gated sodium ion channels and voltage gated potassium ion channels, their role in generation of action potential. In this diagram you can briefly explain the same what is happening here. So this is the different phases of the resting membrane potential. Initially the membrane potential is at minus 70 millivolt. The reason for minus 70 millivolt resting membrane potential is because of 2 or 3 reasons. That is the presence of sodium potassium ATPase pump pumping out more positive compared to pumping in less positive, creating negativity inside the cell. The second reason for resting membrane potential is efflux of potassium through leaky potassium ions. So positive charge is moving out, the interior becomes negative. So these two reasons will explain the negativity inside the cell at the resting state before the application of stimulus. So now at point A, when a stimulus is applied, what is happening? From point A till point B, from A to B, what is happening? There is slow deviation from the resting membrane potential. You call it as depolarization. Slow depolarization is happening from point A to B. This is because of leakage of sodium ions from exterior to interior through sodium leaky channels. So the cell membrane permeability to the sodium increases compared to potassium with the application of stimulus. So when the membrane is stimulated, the permeability of the sodium will become more and sodium starts entering into the cell through leaky sodium channels. So that is how the membrane potential from minus 70 is taken to minus 55 millivolt. That is the firing level. So the reason for the depolarization, slow depolarization between A to B is influx of sodium ions through leaky sodium channels. At firing level, what is happening? At firing level, there is something called all or none phenomenon, all or none principle. That means all the voltage gated sodium ion channels which are present in that region will get into active state. So all the voltage gated sodium ion channels will get into active state. That means which is the active state here? So this is the active state here. So this is the active state of voltage gated sodium channels. Activation gate is getting opened. So so there are millions of voltage gated sodium ion channels in that area. When all the voltage gated sodium channels are getting activated, what is happening? There is rapid influx of positive charge. So there is more flooding of, you call it as flooding. What is that? Rapid influx of huge amount of positive charge, sodium influx is happening because of activation of voltage gated sodium ion channels. The sodium ion channels activation gate is getting opened. So that will take the membrane potential from firing minus 55 to plus 30 millivolt. And by the time C, that is plus 30 millivolt, the voltage gated sodium ion channels will go into the inactivation state or inactive state. In this inactive state, the inside gate is closed. So that there is no further influx of sodium ions. So this is the inactive state. And slowly, simultaneously, at this point C, voltage gated potassium ion channels will start opening. Voltage gated potassium ion channels will start opening so that the positivity is taken out. So that is restoration of polarized state is happening, so that more and more potassium efflux, the inside becomes more and more negative. So there is a rapid repolarization up to D, followed by continued potassium efflux along the concentration gradient, slow repolarization from D to E until the membrane potential is restored, and still further continued potassium efflux will result in hyperpolarization from E, that is the resting membrane potential minus 70 millivolt, to minus 75 millivolt F, hyperpolarization, continued potassium efflux, and followed by restoration of resting membrane potential. Thank you.